So in previous videos, we introduced the band structure diagram, or the band diagram, also known as the EK diagram, and we talked about a couple different limiting cases here. One with the large bandwidth represented by W here, so that's a big energy gap between the fully bonding and the fully anti-bonding state from 0 to pi over A for the wave vector, and then one where we have the smaller bandwidth. And it's important to conceptualize this. Like, what is this EK diagram, this band diagram actually representing? Well, it's essentially an MO diagram for every point in space. This is a single band being represented here, but you can imagine if you had multiple bands stacked on top of each other, this is drawn as a line, but what it's essentially representing are discrete states, just like you would produce in a molecular orbital diagram. And so you essentially have all molecular orbital diagrams represented for crystal or crystal orbitals for over all k-space, which we know to be, because it's sinusoidal, from 0 to 2 pi, but it's symmetric here, so we can just plot the 0 to pi over a. So that's really an important way to conceptualize this. So this is an MO diagram, but essentially an infinite number of them stacked on top over this entire space. That represents the entire crystal. And in 3D crystals, remember this is for like a one-dimensional line of the simplest possible hydrogen atom orbitals, but in a 3D crystal, particularly one with a complicated crystal structure, one that's not just like a simple cubic, which is most crystals, these band structure diagrams get pretty complex. And the additional complexity comes in part because there are more bands. There's going to be one band for each of the atomic orbitals in the unit cell. So if you've got heavy atoms that have, 1s, 2s, P's, D's, all the way up through F's, then you get really complicated diagrams. And in fact, a lot of materials scientists and materials chemists will start to call those spaghetti diagrams because there's just a bunch of interweaving lines, each one representing a different band originating from the original atomic orbital in the atoms comprising the crystal structure. And because of this complexity, this increasing complexity, the utility in band diagrams starts to be diminishing. So if you have more complicated crystals with more than one atom that are heterogeneous, especially heavier atoms with lots of atomic orbitals, they become really difficult to interpret. So one mechanism for depicting the electronic structure in a simpler format is to convert these band structure diagrams, these spaghetti diagrams that are really complicated, into these things called density of states plots, or DoS for short. All right, so let's define this density of states plot. And so the idea of density of states really just is a representation of the density, literally the number of electronic states at a similar energy within that volume that you're describing, within a cubic centimeter or whatever. And so I've got our original EK diagrams for the wide bandwidth and the narrower bandwidth examples. And then I have blank density of states graphs here. So we'll build them up for both of them. And you can see what's really handy is that the y-axes are the same. So those translate identically. So we're talking about the energy then of those states, right? This is every point on these curves in the EK diagram that represents a molecular orbital diagram. And so and those are just states inside that crystal lattice. Those are states that an electron can exist within. And so that energy translates directly into the density of states plot. What changes is this x-axis, which is the density of states. It is this thing that I just described. It's the number of those states per unit volume. And so if you have more of those states at that energy, then it would be increasing to the right on the x-axis. So the energy is still the same, but the number of states represented at each one of these points is increasing. And so if you were to zoom in to this blue line here, and we know that this represents actually discrete states, just with really, really small energy gaps between them. But if we thought about those as little points, right, the number of points would correspond to the density of states. If we have more points comprising that line, we have more states available at that energy. on the y-axis, and so we would have a spike or an increase in the density of states corresponding to that energy. And so you can kind of think about it this way. So like if it's where you have more states available at that same energy, then the flatter the EK diagram, right? If the flatter the region of the EK diagram, that means we've got lots of different states here, right? Because we're changing K, but the energy isn't changing much, right? And so if we're thinking about the density of very similar energy states, then flatter means we're staying at the same energy or nominally the same energy, but we have more available states. So flatter regions corresponds to an increase or a peak where we have something that's sitting out further to the right in the density of states. We've got lots of crystal orbitals with similar energies. And in contrast to that, the steeper regions, like this middle region in the EK diagram, we are changing energy really quickly, right? The slope of this region is changing at very small changes in K, which means we have a lower density of states available as we spread them out over a wider energy range. And so just to reiterate, flat regions correspond to higher density of states. Steeper regions in our EK curve correspond to the lower density of states. And that's how we translate the two. So let's build up the density of states for this first one, knowing how we translate between EK and density of states. And so first thing we can do is just think about what are the boundaries of energy? And the boundaries of energy in our states are still the same energies, right? The axes are the same. And so that means the bottom energy would be the lowest energy for the band, which was at K equals 0, and the upper energy would be up here at that antibonding state where we have K is equal to pi over A. Similarly, we would expect that in the flatter region of the curve, which is when we're deviating from 0 at the early parts and also again right at the tail end, as we approach pi over A, that's when we'd expect the maximum density of states. So I'm just going to make a mark here, and we'll just assume this is symmetric for now. It's not, and it won't be almost ever, but just for simplicity here, we're talking qualitative translation between the two. And largely what we want to be able to do after this is interpret density of states. What does this actually mean in terms of the available orbitals for electrons to move within? And so that would be maybe similarly up here. But at this point in the curve, we are steeper, right? And so we're traversing energy space over similar K, which means that we don't have as many available to us. And so we start to inflect somewhere in here. And so we can start to just generally sketch this out by connecting these red dots on our density of states. So we get something that nominally looks like this, where maximum number of density of states, the maximum number of states per unit volume, is going to be where we have the flatter regions at the low values of K and the higher values of K. And then as we change our energy pretty rapidly here, we just have less states available over that energy range. And so we start to dip in here and we end up with a shape that looks like this. So density of state plots provide information about energy levels, as we've described here. That sets the bounds of the low and the high, which is the same as the EK diagram. The filling, which I've filled in here, and so our band is actually half filled completely, so we shade in up to the energy at which it's no longer filled, and this empty section indicates to us when we look at a density of state plot that those are not filled. And this we know because it's half filled. It's a half filled band because we're getting one electron from each of the 1s orbitals in our linear chain of hydrogen atoms. And so when you look at a diagram like this, it's just really coming from the valence electrons. So we've got our anti-bonding half and our bonding half, and we filled up the bonding. We have empty anti-bonding, and so in a lot of ways, and we get the width of the bands, which really tell us how many electrons can reside in those states. And so we get a ton of information from this without having to really think about K or block functions for that matter. I think it's important to know where these come from, and it can be useful to generally look at a band structure and know that it comes from somewhere and that it tells us something, but it takes a lot more practice to understand exactly what it means. Density of states, we can get there in a shorter period of time and develop intuition. And in a lot of ways, the density of state plots is the closest thing to a molecular orbital diagram that we have for the solid state. And just like we can look at molecular orbital diagrams and pretty quickly understand where things like the frontier orbitals are, right? Like where are the most reactive orbitals and where are the most reactive electrons, that being the highest occupied and the lowest unoccupied molecular orbital. This is essentially telling us the same thing, because we're finding out that this is the highest energy electron that's occupying a state in the band, and this gets a specific name, and it turns out to be just incredibly important. And so it's one of those really super duper important things. We call it the Fermi level, or the Fermi energy. I was raised calling it the Fermi level, so you'll hear me calling it that a lot, and it gets denoted as E sub f. And it is the energy of the highest occupied electron state, which is essentially like the HOMO, the highest occupied molecular orbital, in a molecular orbital diagram. And so we have a lot of our chemical intuition that helps us understand this. So that's what's nice about it. In fact, it's possible to sketch approximate density of states plots from simply the knowledge of the structure, the electron count, and the rough orbital energies in a lot of the same ways that you can approximate MO diagrams, right? Like if you wanted to compute an MO diagram, we could do that. We could compute it and do that from first principles. Or in an inorganic course, in like a Chem 275 course, you might have sketched out the orbital diagrams from basic symmetry arguments and basic orbital mixing arguments. The same can be true of density states. So it's a really nice intuitive physical representation of what's happening in terms of the electronics in the bands in these solids. It's also important to note in terms of this Fermi level that if the Fermi level bisects a band like this, right, we've got this band, and from that we have this sort of contiguous density of states. If it bisects this, this is typically what metallic behavior is, meaning you have something conductive, because it means that we have available states at infinitely small energy gaps above where our highest occupied electron state is. Meaning, if we have thermal contributions from the world, which we do anytime we're above absolute zero, then that means some amount of these filled states, represented by the shaded region, could easily just bump themselves up into this space, and that is what gives us conduction, right? That's mobility. Of course, if we have more states available, which would mean this would spread out further to the right, which would mean a flatter band, that would become even more metallic because we'd have more states at that particular level. At this point, we're starting to decrease the number of states available. We're kind of in the bottleneck of the band, given the shape of this band structure. And so while this is likely conductive, it's not as conductive as it could be if the density of states were further out here to the right. So let's contrast that picture against our other example, and remember from previous videos that this EK diagram, this band structure diagram, still came from the linear chain, the 1D chain of hydrogen atoms, but we separated them further. So we put them 2 angstroms apart instead of 1 angstrom apart. So less overlap means less of a difference between the bonding and anti-bonding state. And so that gives you a flatter band. So flatter band, steeper band. Smaller or narrower bandwidth, wider bandwidth. Those are the differences. They're the same exact system. All we've changed is the last parameter, how much of an overlap we get, which, remember, is a proxy for how strong the bond is, how strong the interaction is. And so I can fill in the density of states in the same way that I did before. The upper and lower bound energies of the band are defined by the EK diagram. So here's my lower, here's my upper. That is the same as the lower and upper bounds of my density of states diagram. We still have the same number of valence electrons being contributed, so we have a filled bonding state and a completely unfilled anti-bonding state. The major difference here is this huge flat region. Where we have a flat region, the flat region gives rise to a lot more available states at each one of those energies. And so we get less of the this stark decrease in the density of states in the middle of our band, and we get a little bit of a trade-off. The flattest parts are still at the beginning and at the end of the band. We still have some inflection here, but not as much. And so that's the difference in these two. And so as the flatter this band becomes, we have more or higher density of states, and this becomes more metallic, more conductive, because we have a higher population of empty states just above this that thermally can be accessed by the population of electrons here. And so in both cases, like if you integrated this, it's the same, but the number of unoccupied states is way up here at higher energy, which are probably thermally inaccessible. Whereas down here, there's a much higher number of those states just above the Fermi level. And so that would make this a better metal. Let's compare one more pair of band structure diagrams and density of states diagrams. So we've already sort of described the evolution of these two and said that this first one is probably still a metal because the Fermi level bisects the band. But there's not a ton of states available thermally if we just start exciting this, right? We're at the narrowest point in the density of states, but it's still conductive. So we'll call this a poor metal. And then we said, well, we've got this where the bandwidth is narrower, so we've got more available states over this narrower range, and this is a better metal. So this is what we consider a good metal. Now let's look at this third case where we have another like limiting extreme in our band structure diagram. So we start down here at k equals 0, and then we have essentially this delta function, this inflection point where we nearly have a monotonic increase in E, and then it flattens out. What do we get for our density of states plots, given what we know about the general shape of the density of states as it relates to the EK diagram? And then what would we categorize this? So I'd pause the video, stare at this for a little bit, and really think about, how do I translate this? And then what would I call this, this type of material? So I took the liberty of sketching in the density of states here, and hopefully you came up with something similar where we have this, the flat part of the band here, which is completely flat in the extreme. We have a very high density of states, but it's really narrow. And then where we have it go vertically in the EK diagram, we have absolutely no points here, or no states available within the density of states. And so there's nothing here. And then at the top it flattens out again. And we have fully occupied the bonding band and an unoccupied anti-bonding band. And so hopefully this is jogging some memories, which is that this represents the density of states and the EK diagram of a semiconductor. And I have labeled the Fermi level or the Fermi energy right in the middle between the two bands, which is coincidentally or not coincidentally the band gap of the material. And the reason it's here and not at the highest occupied energy state, which is how we defined it, is that's true when you have the Fermi level in a partially filled band. But when you have two bands where one's filled and one's unfilled, which is the case for an intrinsic semiconductor. Remember, we're talking intrinsic here, not extrinsic yet. The Fermi level changes as a function of the dopant concentration or dopant density. But in an intrinsic semiconductor, the Fermi level is technically defined at 0 Kelvin, absolute zero. And so at non-absolute zero configurations, which is all real things, there's some population of holes that form because there's some population based on the Maxwell-Boltzmann distribution of electrons that actually can thermally excite across the band gap. All that to say, there's some fancy math that gets you to a Fermi level here for an intrinsic semiconductor, which is halfway between the occupied and the unoccupied band, or right in the middle of the band gap. So we can just be okay with that, I think, without deriving it, because it's not going to be of much utility. What would be of utility is just knowing, though, that the exact position of this depends on how many carriers and what types of carriers you have. And so this Fermi energy is something that we can control. Similarly, if you're an electrochemist like me, this is my training, when you apply a voltage to an object, whether it's a metal or a semiconductor, what you are doing exactly, what you are literally controlling is this Fermi energy, the Fermi level. And so if you apply a negative voltage to a metal in solution, you are actually taking the average energy or the highest occupied state energy and increasing it. That's more negative. In this space, it's higher energy, and you can lower this by making this more positive. That's what electrochemistry is. And we can also do semiconductor electrochemistry. Same thing is true. You can apply voltages to these things, and what you're doing is modulating the position of the Fermi level or the Fermi energy by either adding energy or decreasing the energy in the form of the electric field or the applied potential that you're applying.